Modern computer networks execute trillions of operations per second, relying on hardware packed with billions of microscopic components. Processing data at this density makes physical relays or vacuum tubes obsolete. Computing requires a switch controlled entirely by electrical signals, with no moving parts. The first successful and reliable solid-state switch was the Bipolar Junction Transistor, or BJT. While the BJT made solid-state electronics possible, engineers trying to pack more of them onto a single chip quickly encountered a physical limitation. This barrier threatened the continued scaling of computers. The bottleneck lies in the BJT's operating principle. It is a current-controlled device. To keep a BJT switch engaged and conducting, a steady stream of physical charge carriers must flow continuously into its input terminal. Forcing physical particles through a material generates heat at the atomic level. A BJT constantly draws power and bleeds heat for as long as it remains on. Placing 1 billion of these on a single silicon chip would produce enough thermal energy to melt the hardware. To achieve high-density computing, engineers had to shift from current control to voltage control, manipulating electric fields instead of flowing particles. Switching logic states using only electric fields is the specific physical reason a smartphone can operate without suffering from thermal runaway. To see why this heat is unavoidable, we must look inside an active NPN BJT. The BJT has 3 regions: emitter, base, and collector. The emitter base junction is forward biased, while the collector base is reverse biased. Electrons push into the thin base, diffusing across into the collector. Collector current equals input base current multiplied by beta. Because the base emitter junction must be forward biased, it demands an active, continuous input current. This results in a low input impedance, creating a thermal penalty for high-density transistor scaling. The engineering alternative to this thermal trap is the junction field effect transistor, or JFET. Unlike the bipolar transistor, the JFET is unipolar. It relies strictly on majority charge carriers moving through a single continuous channel. An N-type silicon block forms a channel between source and drain, with P-type gate regions on either side. Applying a negative reverse bias to the gate generates an electric field. The depletion regions widen, squeezing the conductive pathway for electrons. Because this gate junction is reverse biased, it blocks the flow of physical particles. It draws effectively zero continuous current, raising input impedance into the megaohms and slashing power consumption. So how does this widening depletion region act as a functional switch? As the gate voltage becomes more negative, the depletion regions grow deeper into the channel, increasing resistance. Eventually, at a specific negative voltage, the 2 regions meet in the middle. This state is called the pinch-off voltage. At pinch-off, the drain current is either held constant or cut off entirely. The JFET proved that an electric field could control a circuit without drawing massive current. However, it still relies on a physical PN junction at the gate. If an unexpected electrical spike forward biases that gate, the junction catastrophically fails, immediately drawing a massive, destructive surge of current. The engineering solution to the junction problem was the metal oxide semiconductor FET. We take the base silicon channel, remove the P-type gate regions, and cover the surface with a uniform layer of silicon dioxide, a highly effective insulator. Finally, we place a solid metal gate terminal resting directly on top of that oxide layer. This insulated structure acts like a parallel plate capacitor, completely separating the gate from the active channel. Applying voltage accumulates charge on the metal gate, projecting an electric field through the silicon dioxide to attract electrons in the substrate. By utilizing the oxide layer, the physical junction is removed. The input impedance increases to near infinite gigaohms, creating a pure voltage-controlled device. The insulated oxide layer enables a distinct operational state, enhancement mode. In an enhancement mode device, when zero voltage is applied to the gate, the path between source and drain is physically broken. The transistor is off. A conductive channel only forms when positive gate voltage pulls electrons to the oxide boundary, forming a bridge. For binary logic, a normally off state ensures that holding a logic 0 requires absolutely zero holding energy. This default off capability changes the transistor from a continuous, power-hungry analog amplifier into a low-power binary switch. The utility of this switch is realized in complementary metal oxide semiconductor logic, or CMOS. CMOS pairs an N-channel and P-channel MOSFET, controlled by a shared input line. When input switches high, the NMOS turns on to ground, and PMOS turns off. When input drops low, the opposite occurs. PMOS connects to power, and NMOS turns off. Because one transistor is always completely off in any steady state, there is never a direct path from power to ground. The circuit draws virtually zero static current. The invention of the BJT proved solid-state logic was possible, but its reliance on continuous current injection produced too much heat to scale. By utilizing the insulated gate of the MOSFET and layering those components into the CMOS architecture, engineers successfully decoupled processing power from thermal destruction. Today, billions of these microscopic voltage-controlled switches are able to operate simultaneously on a single sliver of silicon. The shift from current to voltage control is the physical foundation of the digital age.